Okay, so the mesh current method is more systematic method and than the applying KVL and KCL and so on and so forth. So we can use the mesh current method. So the mesh current method, as I told you, that it is based on the knowledge of essential nodes and essential branches. So let's consider again this circuit. And we have to figure out the number of essential nodes. So you see there are two essential nodes. Essential node A and this is essential node B. Okay. And of course, one of the essential nodes has to be considered as reference node. So we consider this as a reference node. And so we can write this as the number of essential nodes. Number of essential nodes, which is represented by NE, so it is 2. Now, how many number of essential branches? Because the mesh current method also take care of the number of essential branches. So any branch which connects two essential nodes is considered to be essential branch. So you see here this branch. So this is essential branch. You see here this one, the branch through R3, resistance R3. This is another essential branch. And what about this? This is also essential branch. So there are three essential branches in this circuit. So number of essential branches. So I can write this is with letter B, E, number of essential branches. The next stage is to determine how many equations do we need. So the number of equations, it should be equal to BE minus NE minus 1. So we can write this as 3, 2 minus 1, which is equal to 2. So we need two equations in the mesh current method. So as I told you in my earlier talks, that a mesh is the simplest loop where there is no other loop inside that. So mesh is something like that. And a mesh current is the current that flows through the parameter of that loop. So we have to consider two mesh currents in order to solve this circuit. So since there are two equations that are needed, so we have to proceed like this. So this is mesh 1 and this is mesh 2, or loop 1 and loop 2. And let's assume that we have these two currents, and IA and IB are referred to as mesh currents. These are not necessarily be the real currents. These are some, how you can say, fictitious currents, because the branch currents are there, I1, I2 and I3, and with the help of these fictitious currents we can later solve for I1 and I2 and I3. So let's consider IA and IB are the two mesh currents. And for this, just we have to write the equations. So apply KVL to this loop, having this IA is the mesh current. Applying KVL to this loop, loop number 2, having IB is the mesh current. So first, applying KVL, and if you, of course, you remember that KVL is nothing but the sum of the voltage drop is equal to sum of the voltage rise. So here, when this current is flowing through the source, the voltage will rise. So voltage rise V1 is equal to, when the current, this IA, flows through this resistance, the voltage is dropped. So we can write this as IA R1. Now when the current is going through this branch, this is IA, but another current IB is flowing there. So these two currents are opposite in direction. So you can write this as IA minus IB. So this will be the net current that is flowing through this resistance R3. So if you multiply this with this R3, this will be the voltage drop. Now, applying KVL to this loop. Again, if you just look at this one, considering the direction of this IB current, so the current is flowing from the positive terminal to the negative terminal. So when the current is flowing from the positive terminal to the negative terminal, we consider that as voltage drop. So here, no voltage rise, V2 is the voltage drop. Now when the current is flowing through this resistance R2, of course, IB into R2 will be the voltage drop. IB into R2 will be the voltage drop. And what about here? Current is flowing like this. This current is flowing in this direction. So the net current, while considering this loop, then the net current will be equal to IB minus IA. So IB minus IA into R3. So this will be the voltage drop. Simplifying this expression, we can just take this V2 in this to the right hand side of this equation. So we can write this as minus V2. And a little bit simplification of this equation. We can just take IA as common, so we will have R1 plus R3. R1 plus R3 IA and minus R3 into IB. Here you see minus I3 IA into R3 and IB R2 plus R3. So from this expression we can write this as minus R3 into IA plus R2 plus R3 IB. Now we have these two equations, and you see this is somehow more systematically written as compared to the first one. So with these two equations, we will definitely compute IA and IB. And once we know this IA and IB, we can determine I1, I2, and I3. How? Because you see, IA is equal to I1. So IA is equal to I1. IB is equal to I2. And what about I3? I3 is equal to IA minus IB. So IA minus IB is equal to I3. And once all these unknown are computed, then you can easily compute the power dissipated in R1, R3, R2, or the power delivered by V1, or V2, or whatever the other parameters needed to compute in the circuits.